This is part 2 of my presentation on Adam Harrison's PhD work about a numeric tensor framework. So in this part, I'm going to look at the numeric tensor software proposed by the thesis, or the constructivism, and then I'm going to discuss some illustrative applications, the exemplars that we use to argue for the numeric tensor framework. Constructivism refers to the proposed numeric tensor software. We started by reviewing software packages available in the literature and online. We identified 8 different software packages, and from that we looked for characteristics that generalize what people were after who are working on software beyond the matrix vector paradigm. So in that respect, we wanted comprehensiveness with respect to algebraic aspects. So this included support for higher degree higher degree variables, also entry-wise products, and then linear inversion. Another aspect, programming efficiency. How easy is it to write some code that easily implements a model? Computational efficiency. How fast does that code run on a computer, and that with reasonable amount of memory? And then with the matrix vector framework, we're interested in the case of sparse matrices and vectors because you can accelerate computation. So how do we do the same thing for a tensor framework? The main packages of interest here are highlighted with respect to, in this table, with respect to these different criteria. So comprehensiveness. Now, of course, we are interested in comprehensiveness with respect to the algebraic characteristics we identified of interest, right? So certainly when we develop our own software, it's going to fit that better. But in addition, sparse support is one of the differences between the software we looked at. So the MATLAB Tensor Toolbox, as it's called, it's actually not by MathWorks, but by Sandia National Labs, provided a good sparse support for its high degree approach. And then Blitz++, this was an example more suitable for C++, also provided sparse support. Our approach involved 2 different software libraries. One was for C++ users, and this is computationally fast. It's called libnt. The other one we called NT Toolbox. It's for MATLAB, and it actually interfaces. It's a set of wrappers for libnt. So comprehensive support. We want to support all possible inner, outer, and entry-wise products across numeric tensor operands of any degree. We want to support linear inversions. And one of the challenges here is when we deal with high-degree data structures, not just matrices or which can be represented as second-degree, degree 2 scalars. Depending on tensor degree, the kinds of operations that are possible, if you just talk about inner and outer products, it's already factorial. It grows very fast with the tensor degree. Now, we know that we can map any inner-outer product combination to matrix products. But what's different here is we wanted to put entry-wise products on an equal footing. That adds more possibilities. There are 3 kinds of ways that the indices of a higher degree tensor can interact with the indices of another high degree tensor. And so more complexity and also requires a different solution. So what solution did we come up with? We developed this 3D structure called the lattice. So we can map any tensor product to a sequence automatically. We can do this automatically and map the result back to a sequence of matrix products. So if you have some, here in this case, this shows a scalar multiplication between 2 tensors A and B, each with 3 indices. And the result is, based on the index pattern, the result is also a tensor with 3 indices, a degree 3 tensor. So which indices are undergoing an inner product, which ones are undergoing an outer product, which ones are undergoing an entry-wise product. We can map automatically to a sequence of matrix products where each matrix has the same number of rows and columns. And you can see that here. So all of these are done, theoretically, they could be done in parallel, and then we can map the result back. So programming efficiency to support the NT algebra without much, coding difficulty, right? This is about the readability of the code compared to the model, the algebra. So if you had an algebraic expression like this, in libnt, it will look like this, right? So of course we code on a line with just ordinary characters available on the keyboard. So we have to map the subscripts and the underlines to suitable way of typing that expression out. This is resolved at compile time in C++, and Adam did a great job exploring features of C++ called template metaprogramming. In the MATLAB version, the NT toolbox, which has a set of wrappers that invoke the libnt libraries, we resolve the algebra at runtime using string processing. So you can see here that the subscript arguments are actually all strings enclosed in single quotes here for MATLAB. And so that is then parsed, and then the appropriate libnt code is executed. Okay, so computational efficiency. So one of the things we looked at first is the case of dense tensor decomposition algorithm, the CP decomposition, which is a generalization of SVD. And this algorithm involves multiplications of high-degree tensors, including entry-wise products. So in this case, comparing libnt, which was designed for C++ users, to Blitz++, libnt outperforms it. So you can see here in these tests, as the tensor size increases, you can see the time here, and faster is better, right? So the libnt being the lower red line is faster compared to Blitz++. Now, comparing the similar types of products with the MATLAB Tensor Toolbox against the MATLAB Tensor Toolbox using NT Toolbox, our approach, what you'll notice is that for larger operands, the NT Toolbox is faster than Sandia's MATLAB Tensor Toolbox. And but one of the reasons here is that lower operand sizes, there's some overhead because of the string processing involved, which theoretically can be overcome. Something else to point out, Sandia's MATLAB Tensor Toolbox it's intended for n-mode notation, does not really generalize. It's not as general purpose as it's more handcrafted for specific stuff related to n-mode notation. The sparse data representation that's popular in the matrix vector paradigm cannot manage the operational complexity we find with numeric tensors, of interest with numeric tensors. So we realized that the best approach is to use simple lists to represent a sparse numeric tensor. Our NT software uses what's called a linearized coordinate format. This makes rearrangement operations, sorting and permutation, faster, and these are highly important operations. So they're faster because they involve a smaller memory footprint behind the scenes. So you see in this figure a comparison of the best and worst case sorting times for a representative operation where we're varying the tensor degree in comparison to the alternative coordinate format. So the linearized coordinate format, there's some variation in the speed, but overall it's always faster than the comparative example here. So permutation is a common operation with sparse numeric tensors. This generalizes transposition. So if you have a tensor here with 4 indices, you could imagine that it should in principle be faster to swap 2 indices versus reversing all 4 indices. This involves behind the scenes moving non-zero entry data as well as indices in memory. So we compared a general sorting algorithm for this purpose, shown in blue here, to an algorithm we developed that exploits a priori information, the structure of exactly the kind of permutation operation you're performing in relation to the existing arrangement of the data, because it's already got a particular ordering from its indices that were there already. So with our radix permutation algorithm, we find that the worst case sorting time is the same as it was before, but the best case sorting time is significantly faster. In addition, we also developed an efficient way to multiply sparse numeric tensors. So our multiplication involves mapping to lattices, sequences of matrices. And we realized that we could categorize the type of sparsity beyond the way that it's normally looked at in the matrix vector paradigm. So we encounter examples of hypersparsity, which manifest in 3 different ways here. So other researchers, for example, those who developed the MATLAB Tensor toolbox, were also aware of advanced levels of sparsity, and they did develop ways to exploit that to have faster computations. But they had a one-size-fits-all algorithm, whereas using our categorization of operands, that leads to, in a binary product, 4x4 possibilities, 16 possibilities. We developed 7 algorithms, or we used existing algorithms but mapped them, and we also developed some variations. And this overall is a poly algorithm for performing this hypersparse or just regular sparse multiplication. So compared to the competitor, the MATLAB Tensor Toolbox, we looked at some benchmarks implemented in the best way using both frameworks. And we find this test involves both permutations and hypersparse multiplication. Because of both the data representation, the linearized coordinate format, as well as the poly algorithm, our numeric tensor toolbox approach was faster at all scales of the test. At the largest scale of data, it took 4 seconds, whereas our competitor approach took 60 seconds. Exemplars refer to the examples that help illustrate a particular paradigm. In this case, we are proposing some that we think would help in advancing toward a new paradigm. So these are our illustrative applications. We drew them from computer vision. They exemplify challenges of special linear mappings. And as you can see along the top row, we identified some operations outside the matrix vector paradigm. So high degree mappings, entry-wise products, ternary inner products, linear inversion, sparsity, differentiation in the high degree sense, and also a nonlinear tensor type operation. So the thesis looks at 3 main exemplars, but the one that I want to talk about is the middle one, the linearized maximum likelihood depth map and albedo estimation. It hits here 5 of these operations outside of the matrix vector paradigm. So this exemplar can be easily understood from this visual slide, this set of images here. So on the left, you see images from the Yale Face Database B. These are of multiple subjects. In this case, we're just showing you one subject, taken always from the same pose, but where the lighting is moving about. And the lighting is known. The direction from which the light is coming from is known. So a technique called photometric stereo, which we didn't invent, allows you to extract from these images. It's a model-based approach. Information about the albedo. It's like at each point here, you have a certain amount of reflectance of light, as well as surface gradient. So there's underlying the interaction of illumination and the subject, there is basically a 3-dimensional shape defined by a surface, right? So we have 3 pieces of information, one for each pixel coordinate. 2 surface gradients, and 1 albedo. And so what we did develop was the best method to extract from this a depth map, and the albedo, of course, we already had, but together with the depth map and the albedo, you could now render images from different perspectives to show that you actually have a 3D, technically 2.5D model. Okay, so how does this work? This is a model-based approach. So there are what are called generators. The generators here are surface patches arranged. You can't see, it's 2.5D because you can't see through a patch to some curvature underneath, right? But each surface patch has a vector that points, that indicates the orientation of that surface patch. And it also has a color. In this case, we focused on grayscale, so just an intensity, right? So the albedo is the color of the patch, and then unit vectors. So they all can be put on a grid, right? They are basically telling you the orientation of that surface patch. So this generator gives you another set of generators, albedo and normals. And from this model of albedo and normals, we can actually develop another model, right? So the generators lead to what are called weighted normals. So the unit vectors here, if we multiply onto them, the reflection here is for grayscale between 0 and 1. We can multiply to the unit vector and we get a weighted normal unit vector, right? A vector has magnitude and direction. So not a magnitude of 1 anymore. We can also get from the normals. The normals are vectors that lie outside of the plane of the image, but instead we could look at what are the surface gradients? So basically, how much does the rate of change within the actual plane of the image itself, right? And they can be computed from the normals or the weighted normals. Okay, so what happens is this generative model allows us to take the weighted normals, gives us all the information. Together with illumination, we can render an image that you would see, right? So given like the light is coming from a certain direction with a certain intensity, this is the image you would see. So you can see here it's like we're simulating the illumination source moving, rotating. But of course, images have noise as well, right? So then the actual image a camera computes or a sequence of images would have, here we've exaggerated the noise, some kind of random noise. We model it as Gaussian zero mean noise. Okay, so the model-based approach to get the 3D, the 2.5D representation from the 2D images, right? We have a model, we're going in the inverse direction. So given a set of images where we know the illumination, we want to, with the illumination and that sequence of images, we want to extract surface gradients and albedo. And then from that, if we integrate the surface gradients, right, it's a 2-dimensional integration, we get the surface. And of course, we also have the albedo, so we can color the surface. Okay, but what happens is one of our major contributions here was we model the noise really well. What is the impact of the noise in the observed data, right, when we do this inverse computer graphics computer vision approach, right? So the noise creates uncertainties in the surface gradients, which you can visualize here with this animation. And when we integrate those surface gradients, we have some uncertainty in the actual shape of the surface. Now, with that model, we developed a maximum likelihood. What is the most likely, given some assumptions of the noise, that it's zero mean and Gaussian, which are good assumptions for cameras, we could actually, with a model-based approach, develop, here's the most likely surface and albedo. Okay, so that worked then. What is the connection to this question of paradigm, right? So that if you use the matrix vector paradigm to solve this problem, we're working with data that is intrinsically 4th degree, but we'll have to flatten it into a 2nd degree form. We'll have to represent entry-wise products using diagonal matrices. So it's not like we can't solve it. This is why our work is about paradigms. It's not about can you solve a problem or not, right? It's about how we approach problem solving, right? So the matrix vector paradigm can lead to errors because it's not natural, right? It's also the code that we use then, it's sort of specific to the language. We have to model these flattenings and etc., right? So in a sense, it is sort of an because it's not a good fit, we describe it as arbitrary. Because there's more than one way you could flatten fourth degree data into second degree form, for example. Okay, so if we use a numeric tensor framework, we keep the data in its natural form. The conversions all happen automatically by the software. So the entry-wise products are explicitly supported. The solution expressed algebraically is then implemented. We have this alignment, right, between your model on paper and your programmatic solution. So it's a transparent process. These conversions are automatic behind the scenes, whatever flattening is required. Well, we map to lattices, right? Okay, so what about the actual, besides programming efficiency, what about computational efficiency? So there's two parts to this. One is actually solving a linear system of equations. So when we looked at solving this using our numeric tensor framework and compared it to the matrix vector framework, we did this with MATLAB, right? MATLAB is very good at solving problems from models from the matrix vector framework, computationally computing the solution, right? So our approach, we used third-party routines through libnt. And actually, MATLAB's the sparse matrices are involved here. MATLAB's sparse solver turned out to be faster than the open source one we use. So as a result, beta here is lower because this is measuring time, right? The matrix vector paradigm here outperformed it in terms of solving the system of linear equations that are sparse, right? But it's not just about solving a system of equations. When you work as a practitioner in technical computing, you also have to construct the systems you want to solve, right? So there's some code required to take the data and put it into the form where you have like some equations to system of equations to solve. So the setup time is what's measured here. And you'll see that using the numeric tensor framework compared to the matrix, our implementations in both, and matrix vector paradigm, not just using MATLAB's, what's available with MATLAB, we could outperform it, right? So for all different sizes of data involved, operand sizes, our framework outperformed it. So this one measures the performance of our NT-surface dense and sparse algorithms and shows the merits of using the NT operations. Apart from the exemplars discussed here in this talk, the PhD thesis also uses the numeric tensor framework to address linear parameter estimation problems and separable nonlinear least squares. We also briefly outline the importance of polynomial systems of equations. This is a major gap in technical computing and potential focus for future work. Returning to Thomas Kuhn, articulating these and other exemplars helps reveal how technical computing can be practiced beyond the matrix vector paradigm. So, conclusions of this work on the numeric tensor framework in particular. We framed technical computing and emerging trends using Thomas Kuhn. There was a far-reaching literature review, and we synthesized this work together using theory of paradigms. So this motivation led us to develop a comprehensive and accessible numeric tensor algebra. It was the first to have support for n-degree data, associativity, commutativity, entry-wise products, and linear inversion. We developed innovative and efficient numeric tensor software. So it was the first computational platform to execute or invert any numeric tensor product. There were novel algorithms that advanced sparse numeric tensor computations. We applied the numeric tensor framework to important exemplars, tensor decomposition, high-degree differential operators related to depth map and albedo estimation, and others.